Hello and welcome to Harmonic Motion homework. This is a quick video to show you how I think that these problems should be done. We're going to just cruise through them. Let's get started with number one. In number one, what you have is looks like a spring mounted on some sort of support, and then here it's not stretched out very far, and then here it's a little more stretched out than here. And what you want to visualize here is like it's here and then it goes down and then up and then down and then up. And what it tells you is that this distance from is 0.5 meters. Okay? So it tells you it bounces up and down, 12 bounces in 6 seconds. All right. So first it says is find the period. All right, so let's find the period. We use capital T for period because it's a period of time. And the period can be defined as the total time it takes to do the number of, now what we say here is this OSC is oscillations. An oscillation is any kind of repeating pattern. So in a pendulum, it's a swing back and forth. In a bouncing spring, it's the number of bounces. And here it says it does 12 bounces in 6 seconds. So if I want to calculate the period, I'm going to take 6 seconds and divide by 12 bounces. And this gives me 0.5 seconds per bounce. Which means that for every additional bounce, it takes an additional 0.5 seconds. So that was A. B says, what's the frequency? Well, the frequency is very similar to the period. The frequency, we're going to use little f for frequency, and that can be calculated by taking the number of oscillations divided by the total time. So in this case, it's 12 bounces in 6 seconds, and that gives us 2 bounces per second. Ooh. That means for every additional second that goes by, it bounces 2 more times. C says, what is the magnitude? Actually says, not what is the magnitude, says, what is the amplitude of the vibration? Well, the amplitude is defined as half of the distance from all the way to the bottom to all the way to the top. So the amplitude, we take the distance from the top to the bottom, and you divide by 2, and we have 0.25 meters. The amplitude is also, could be calculated if you knew the distance from the middle to the top or the distance from the middle to the bottom. Those would both be your amplitudes. D says, if the bob at the end, that's this thing is called the bob, I don't know why. If the bob at the end has a mass of 0.8 kilograms, find the spring constant. Well, here's where we are. In the labs, you decided that the period for a spring can be calculated if you do 2 pi times the square root of m over k. This is the mass, this is the spring constant, this is the period, 2 and pi are constants. And so what we're going to do here is we're just going to plug and chug and see if we can't come up with an answer. The period from part A is 0.5 is equal to 2 pi times the square root of, the mass was 0.8, and we're actually trying to calculate the spring constant. So it takes a little bit of algebraic skill here. The first thing I'm going to do is divide both sides by 2 pi. Now, you got to be careful when you do this, because if you just type 0.5 divided by 2 pi in your calculator, it might divide by 2 and then multiply by pi. So either do 0.5 divided by 2 divided by pi, or do 0.5 divided by parentheses 2 pi close parentheses. Either way, when you do that, you're going to get 0.08 is equal to the square root of 0.8 over k. Now, once I have this, I need to square both sides to get rid of that square root sign. So I have 0.0064 is equal to 0.8 over k, which is the spring constant. I'm going to multiply both sides by k and divide both sides by 0.0064. And I got k is equal to 125, and that's newtons per meter. Now, if you get 126 or 127 or 128 or 124, that's fine. It depends on how you round it, but this is the general idea. So that's D. E says, how would the period change if the mass were doubled? Well, from the lab or from the equation, you can see that here is your equation. And so there is a square root relationship between the mass and the period, which means that if you take the mass and you do times 2 on the mass, you don't get a times 2 on the period because it's underneath the square root. What you end up getting on the left side, since it's this here, is you'll be times root 2 on the period is equal to 2 pi times the square root of So because the m is underneath the square root, if you were to double the mass, you would only get times root 2 for the period. So they both go up, but this one goes up by a factor of root 2, which is 1.41. Another way to do that is you could go back to this equation here. You could plug in a new mass. Instead of 0.8, you plug in 1.6. You now know the spring constant, and you can compare it to this 0.5, and you can see it goes up by a factor of 1.41. Similarly, I'll do F over here, where I have some room. F says, what would happen if you were to double the spring constant? Same equation. If you want to take k and multiply by 2, again, k is in the square root, and it's in the bottom. So what would happen over here? The period would be divided by root 2. Because when you multiply k, it's underneath the square root, and the sides have to be equal. So what would happen in the period if you double the spring constant? It would decrease by a factor of root 2. All right, that was number 1. That was a lot. Let me reset, and we'll move on to number 2. So number 2 says, underneath the car there are 4 springs that act to cushion the passengers when a car hits a bump. For this problem we will assume that the 4 springs act as a single spring with a spring constant of 65,000 newtons per meter. Alright, so this is number 2. It says we have a spring with a spring constant of 65,000 newtons per meter. This means that if you want to compress that spring a full meter, it would take 65,000 newtons. That is crazy. Says a family of 4 people with a total mass of 200 is riding along in a car which has a total mass of 1,200, hits a bump, which means that the total mass would be equal to 200 plus 1,200, so that's 1,400 kilograms. Says what is the period of oscillation and what is the frequency? No problem. If I want to get the period for a spring from the lab, we remember that it's 2 pi times the square root of m over k. Luckily we know m, we know k, so let's just plug and chug it. This is 1,400 kilograms. This is 65,000 newtons. Calculate that real fast. I'm doing these in real time. So I got a period of 0.92 seconds. Let me check that again. There you go. So the period is 0.92, and that would be seconds per bounce. That would be seconds per bounce. Second question says, what is the frequency? Well, from the last problem, we realized that if you want to calculate the period, it'd be the time divided by the number of oscillations. But we said that the frequency was the number of oscillations divided by the time. And you can see when you look at those that they're obviously the reciprocal, because this is time over oscillations, this is oscillations over time. So if you want to calculate the period, you could just do it by taking 1 over the frequency, or what we need here, the frequency would be equal to 1 over the period. So frequency is equal to 1 over the period, which is 1 over 0.92. And that's 1.0, that's 85, we'll call it, 9. And that's bounces per second. There's the answer to A, here's the answer to B. So once we develop this law in the lab, a lot of this now is just taking the law and plugging and chugging it. All right, let's reset to number 3. Three says the gravitational field strength, little baby g, near the surface of the Earth is 10 newtons per kilogram. However, it depends on the distance from the surface of the Earth. A way cool scientist takes a pendulum to the top of a mountain and attempts to measure the value g. He used a pendulum bob of mass 1.5 kilograms and a string length of 0.4 meters. The pendulum swings with a frequency of 0.787 swings per second. Find the period. Well, it tells us that the frequency is equal to 0.787, and that's swings per second. So to get the period, I'm going to use the same rule we used in the last problem, which is 1 over the frequency. So that would be equal to 1.27 seconds per swing. So B says, find the acceleration due to gravity. So in this problem, we're solving for this little baby g value. This little baby g value is both the gravitational field strength and it's also the acceleration due to gravity. So we use the little baby g value for both of these concepts. Even though those concepts are a little bit different, they end up with the same value. So it's a little confusing, but we're solving for g. According to the lab, we developed this law for pendulums. If you want to find the period, it's 2 pi times the square root of L over g, where L is the length and g is the gravitational field strength or the free fall acceleration. So we're solving for that. We know everything else. Let's plug and chug it. We have 1.27 for the period, 2 pi times the square root of, tells us the mass is 0.4, and we're going to solve for g. So, to do this, the first thing we're going to do is we're going to divide by 2 and divide by pi. And I have 0.202, and that's equal to the square root of 0.4 over g. I'm going to square both sides. So on this side I have 0.041 is equal to 0.4 over g. To solve for g, I'm going to divide both sides by 0.041, multiply both sides by g. I end up with g is equal to 9.76. And that can be meters per second, or we call that newtons per kilogram, depending. They end up equivalent in this case, so it's not a big deal. And what we see is that this is a little bit less than the 10 that we're using, a little bit less than the textbook value of 9.8. So that seems to be a pretty good number for the top of a mountain. All right, let's reset and let's move on to number 4. Number 4 says, originally, when a group of really smart people got together to make up the metric system, they defined 1 second as, in quotations, 1/2 the period of a pendulum with length 1 meter. Find the period, use 3 decimal places of a pendulum with length 1 meter, assuming that the g value is 9.8. Okay, so we're using a pendulum, so period of a pendulum is equal to 2 pi times the square root of L over G. So we're just going to plug and chug it. They say use 1 meter, and they want the G value is 9.8, and they want 3 decimal places on this. Okay. So let me get my calculator. So I'm going to take 1 divided by 9.8. I'm going to take the square root of that. And then I'm going to multiply by 2 pi. And I end up with a period of 2.006. And that's seconds per swing. That's the answer to A. And then B says, is the above description a good estimate? Justify your answer. And I would say yes, because the above description says it's 1/2 the period, and if my period is 2.006, and I divide that by 2, then I get 1.003 seconds. And that's pretty good for the idea of what a second is. In the 1800s when they did this, they couldn't measure this far out anyway, so this is a really good estimate. C says, why didn't it tell you how much mass to put on the end? And what did we look at in the lab? That the mass doesn't affect the period of a pendulum. You know how you know that? Because when you look at the equation, you notice that there's no mass in the equation at all. If there's no mass in the equation, then it can't be a factor. Here's a question I really like. It says, D, what would you have to do to the length to get the period to double? So if I have 2 pi times the square root of L over G, if I just multiply the length by 2, because it's under the square root, this isn't going to double. So what would I have to do to the length to get the period to double? And the answer is, I have to take the length and I have to multiply it by 4. Because if you take 2 pi times, if I do L times 4 here, well 4 is underneath the square root, this will give me 2 times the period there. So the answer is, if I want to get the period to double, I need to increase the length by a factor of 4. That is a assessment question if I've ever heard one. Okay, let's get set for 5. Ooh, that red is sticky. Okay, let's do 5. So 5 starts out with a picture. And it has like a platform here. And then we have the same platform sometime later. And then the same platform sometime later. So we took this spring here. And we stretched it out, and it's got a block on the end here. And we pulled it out here, and we're going to let it go. And it's going to slide in, and then come to a stop, and then slide out, and come to a stop, and slide in, and come to a stop, and slide out, and come to a stop. So at some point, it's way out here. And then later on, as it's sliding in, it's sliding in, and then eventually it gets here. So it's super stretched out, and then it slides in, and then it's super compressed, and then it's going to slide back out. And so in the middle here, or when it's out here, the spring is pulling it back. So the force by the spring is inward. Here, when it's compressed, the force by the spring is pushing it outward. And here, when it's in the middle, it's neither stretched nor compressed. So the force by the spring is equal to 0. And this is called your equilibrium. Called your equilibrium position. What's cool about this is that if you were to look at the distance here from the middle to compressed, we would call that an amplitude. Or if you were to look at the distance here from the middle to stretched out, that is also an amplitude. So that's cool. So it says, draw the spring in its equilibrium position. So this is A, this is the equilibrium position. So draw the spring at its subsequent compression. That's B, that's right there. C says, if the spring constant is 10 and the frequency is 0.714, calculate the mass. No problem. I know the rule is, for a spring, is 2 pi times the square root of m over k. I don't know the period yet, I only know the frequency. So the period is equal to 1 over the frequency. So 1 divided by 0.714. Period is 1.4. So if I go to plug and chug this, 1.4 is equal to 2 pi times the square root of m, which is what we're looking for, divided by the spring constant they tell you is 10. So we got to go to calculate this. So I'm going to take my 1.4 divided by 2, divide by pi, square it, and multiply by 10. And I got that m is equal to 0.5 kilograms. And that's C. And then E says, nope, D says draw energy pi for the mass at the 3 locations. No problem, I love a good energy pie chart. So if I draw them for the 3 locations, I'm going to need 1 when it's totally compressed, 1 when it's at equilibrium, and then 1 out here when it's stretched out. Within my ability to draw those to the same size. Well, when it comes out here, it slows to a stop and then speeds up going back, which means that out here it's all elastic energy. As it cruises back through the middle, it's moving fast, so this is all kinetic energy. Because the spring isn't compressed or stretched out. And then what do we have here? It's back to all elastic energy because the spring is totally compressed this time. In between these, the only thing that's changing the way that the energy looks is a force by the spring. That was 5. Okay, let's reset for 6. A pendulum with length 1.2 meters and a bob on the mass 3 kilograms is set on the moon where G is equal to 1.6. Ooh, find the period of oscillation. This is so cool. One of the things I think is super cool about this is that they actually did this on the moon. They didn't know the G value on the moon, and so they took a pendulum with them. They took a pendulum, they set it up, they knew the L and they measured the period and they solved for the G value. That's how they figured out what G on the moon was. This one, we're actually just using these pieces of information. So we're just going to plug and chug this one straight up. 2 pi times the square root of, it says it's 1.2, and on the moon the G value is 1.6. Okay, let's plug and chug this and see what happens. And I got a period of 5.44 seconds. So it would take 5.4 seconds for that pendulum to swing back and forth. So this is A. B says, how would the period change if the mass were doubled? And the answer is, it wouldn't. Because as you're noticing, there's no mass in the equation, so mass is not a period, not a factor in the period of a pendulum. Here it says, how would the period change if the length were quadrupled? Well, if t is equal to 2 pi times the square root of L over G, if I take my L and if I multiply it by a factor of 4, since 4 is underneath the square root with the length, then I'm going to get 2 times the period. So if you quadruple the length, you get twice the period. D says, if the original bob were hung on a spring, what would the constant need to be in order for the spring to oscillate with the same period? So what we're going to do here is we're going to equate our two ideas. We know the period for a pendulum is equal to 2 pi times the square root of L over G. The period of a spring is equal to 2 pi times the square root of M over K. And so there's a couple ways you can do this. So you can take this original period and you can plug it in for the pendulum, the period of a spring. You know the mass and you can solve for K directly. Or one other thing you can do is you can set these two equations equal to each other. If you set these two equations equal to each other, you end up with something that looks like this. 2 pi times the square root of L over G is equal to 2 pi times the square root of M over K. And so, because it asks what would the spring constant need to be in order for the periods to be equal? Well, if the periods are equal, you get this statement. The 2 pi's disappear, you square both sides, and you end up with L over G is equal to M over K. And now we can plug and chug in what we know. It says the length of the pendulum is 1.2. The gravitational field strength is 1.6. It says the mass that we're using is 3 kilograms. And we can solve for K. And we've got a spring constant of 4 newtons per meter. All right, one more. 7 coming up. Obviously the homework is a bit repetitious, which nobody likes, but it will give you a sense of whether you know how to do this stuff or not, for sure. So 7 says, answer the following questions about the spring at the right, justify your answer to each. Oh, this is cool. So basically it gives you a snapshot of a bouncing spring at 3 different moments in time. So in the first one, it's totally stretched out. In the second one, it's basically halfway stretched out. And in the third one here, so down here it stopped, here it's moving up, here it stopped, and then if we kept going it would be down and then to the bottom. So A says, well, let me label it, this is A, B, and C. So A asks, where is the speed of the mass 0 at A and C? That's where it stopped and changing directions. Where is the speed of the mass the greatest? B. Whether it's moving in the up direction or the down direction, that's where the speed is greatest. So it's speeding up to B, and then slowing down to C, and then speeding up to B, and then slowing down at A. C says,
what are you talking at?
I'm talking to the camera, baby. C says, draw a motion map for one complete oscillation, and it says draw energy pie chart. So if we do A, B, and C, okay, let's do a little motion map action. So it's here, then it's here, then it's here, but one of the things we know is that here it's speeding up to here, so it has speeding up. But we also know that symmetry is your friend a little bit, and so it speeds up to here and then slows down to there. So if I look at the way the dots look, it stopped, speeds up, and then slows down, and then speeds up and slows down. So we actually need to go up and come back down. So let me offset this top one. So it's going to start at A. Now, let me use the green for the velocity. Here it stopped at A, and so it's moving slow, moving faster, moving fastest. And then these two should match. And then stopped again, and now it's going the other direction. And then stopped again. And then if I want to look at the acceleration, even though it stopped here, it has a large acceleration because that's where it's most stretched out. So large acceleration, and this one smaller acceleration, and this one even smaller. No acceleration here. And then now it's moving up but slowing down, so it has some acceleration here. Some acceleration here. Huge acceleration here. And then obviously these should match. That one's a little small. Now if we're going to do pies, if we're going to do pie charts, we'll do a pie chart for A, a pie chart for B, a pie chart for C. One of the things we'll do is we'll call this down here our H equals 0, so that means there's no gravitational energy there. So this one is stopped, there's no kinetic energy. It's at 0 height, so no gravitational energy, so this one would be all elastic energy. In the middle, it's moved up some, so it has some gravitational energy. It's moving fast, so it has some kinetic energy, but the spring is still partially stretched out. So this one has all three. We don't have a way right now to know the proportions of them, so I'll just make them equal so we can see them all. Here's the elastic. Here's the kinetic. And gravitational. And the top one, let's assume that it comes and it's fully compressed, or so this is not a compression spring, this is a spring that only gets stretched out. Let's say it's not stretched out at all. So this one's cool because it's not moving either, so it's only gravitational energy. What's cool about this is as it moves up, two things are applying forces, the spring and the G field. And that is it. Hope you enjoyed that.